Now we are starting with a new topic, that is colligative properties. Okay, colligative properties. Now what are these colligative properties? These are the properties of solution that depend only on the number of solute particles in solution and not the nature of solute particles. Okay, so again I am repeating, it is the property of solution which depends only on the number of solute particles and not the nature of solute in the solution. Okay, so we know that a solution is prepared by dissolving a solute and a solvent, right? So colligative properties only depend upon the number of solute particles, means how many solute particles are dissolved in that particular solution. It has got nothing to do with the nature of the solute particles and not even with the solvent particles. Colligative properties, they are just dependent on the number of solute particles and not the nature of solute. Okay, I hope this is clear. Now under colligative properties we are going to study 4 colligative properties. So there are 4 colligative properties. The first one is lowering of vapor pressure. Lowering of vapor pressure. The second one is elevation of boiling point. Of solvent in the solution. Third one is depression of freezing point. Of solvent in the solution. And the last one is osmotic pressure. Okay, so these are the 4 colligative properties that we are going to study in detail. The first one is lowering of vapor pressure. Second is elevation of boiling point of solvent in the solution. The third one is depression of freezing point of solvent in the solution. And the last one is osmotic pressure. Now we move on to the first one, that is lowering of vapor pressure. So we are studying the first colligative property, that is lowering of vapor pressure. Okay, now before going on to our topic, do you know what is the meaning of vapor pressure? So what is vapor pressure? Fine. Now we know that all liquids have the tendency to evaporate. Okay, evaporate means they can vaporize, right? So all the liquids have the tendency to evaporate, and if the intermolecular forces are weak, then the liquid evaporates easily and they are called as volatile liquids, right? If their intermolecular forces of attraction are weak, means what? The molecules won't be held tightly with each other, and that is why they can evaporate quickly. And when a liquid evaporates quickly, what do we say? It is a volatile liquid, right? For example, chloroform is a volatile liquid, or the acetone that we use to remove the nail paint or the nail polish, that is a volatile liquid. So in these liquids, the molecules, they are held by the intermolecular forces of attraction very weakly. Okay, there is very weak intermolecular force of attraction between the liquid molecules, and that is why they evaporate quickly and they come under the category of volatile liquids. Okay, now if I take a beaker, fine. In this beaker, say there is a liquid, okay, so there will be molecules that will be present here on the surface, right? And there will be molecules that will be present in the bulk means you can say inside the solution, okay. So these are the molecules that are present on the surface, and these are the molecules that are present in the bulk, or you can say inside the liquid. Now why it is called bulk? Because if you look at these molecules, then they get force only from the molecules which are present downwards, okay. From upper part they do not get any force of attraction, so they get the force of attraction only from the molecules which are below them, whereas these molecules which are inside or in the bulk region, they get the pull or force of attraction from all the possible directions, okay. So now when vaporization takes place, the molecules which are at the liquid surface, so these molecules, they are going to start evaporating first, so they are going to get converted here in the gaseous phase, right? Now if I take the same beaker and if I add the liquid in there, again you have the molecules present here at the surface, okay, and you will be having molecules inside as well, okay. Now if I place a beaker on this, a lid on the beaker, what is going to happen? Now also the molecules which are at the surface, they are going to evaporate or they are going to vaporize. But what is going to happen? Because of this lid here, or because of this cover here, these vapors cannot escape out of the beaker. So what is going to happen? They will go up, they'll come back again. They are going to exert pressure on the walls of the beaker as well, okay. So they are going to collide with the cover or the lid, they are going to collide with the walls of the beaker, and they are going to come back. And I told you a point is going to come that the number of molecules that are getting converted into gaseous phase, they condense back and come back into the liquid phase as well, right? So for example, you can take the hot cup of tea, and if you cover that with the saucer, what happens? You will see that the vapors are coming out there, and when you lift it up, you will see those vapors getting condensed back into liquid as well, right? So a time comes when your rate of evaporation becomes equal to rate of condensation, okay. Evaporation means what? The liquids are getting converted into gaseous phase, okay, and condensation means what? The gaseous form again getting converted back into liquid phase. So the rate of evaporation becomes equal to rate of condensation, and that is when you can say that equilibrium is achieved. Equilibrium is achieved. So when is equilibrium achieved? Basically when rate of evaporation becomes equal to rate of condensation. So how are you going to define this vapor pressure now? So vapor pressure, it is the pressure exerted by the gaseous state of the substance when it is in equilibrium with solid or liquid phase, okay. Again I am reading it. Vapor pressure, It is the pressure exerted by the gaseous state of the substance when it is in equilibrium with the solid or liquid phase. Now here I gave you the example of liquid phase, right? So the pressure, so this area, the pressure which is exerted by the gaseous state when it is in equilibrium with that of the liquid state. And when is that possible? Only when your rate of evaporation becomes equal to rate of condensation. Okay, so vapor pressure, so this pressure that is exerted, okay, means the rate of evaporation when it becomes equal to the rate of condensation is when vapor pressure takes place. Okay, so it is the pressure exerted by gaseous state of a substance when it is in equilibrium with the solid or liquid phase. Okay, I hope you are clear with what is vapor pressure. Now one experiment was performed wherein they took a non-volatile and non-ionizable solid which was dissolved in a liquid solvent. Okay, dissolved in liquid solvent. Okay, so they took a non-volatile or non-ionizable solid. Now what is non-volatile? Non-volatile means it is supposed to have strong intermolecular forces of attraction, so evaporation is not possible here. Okay, and they took a non-ionizable solid. Okay, it was non-volatile and non-ionizable. Now what is the meaning of ionizable? Ionizable example is NaCl, means they split up into their own ions. Like we know it is going to split up as Na plus and Cl minus. Okay, now non-ionizable means what? For example, C6H12O6. Now this is an example of glucose, right? So we know that it is not going to split up as C, H plus and O minus. Okay, this is not possible, hence it is non-ionizable. Non-ionizable means what? It is not going to split up into its ion. Okay, so the solid that they took, it was non-volatile, means it was not going to evaporate, and it was non-ionizable as well, means what? It was not going to split up into its ion, and they dissolved this solid in a liquid solvent. Okay, so basically they took a beaker and inside the beaker they added the non-volatile non-ionizable solid and they dissolved it into the liquid solvent. Okay, now it was found that the vapor pressure of this solution, okay, the vapor pressure of this solution is lower than that of the pure solvent. Now why did that happen? Okay, again I am telling you, the vapor pressure of this solution was observed to be lower than that of the pure solvent. Now here the vapor pressure of the solvent is lowered by adding a non-volatile solute. Okay, now imagine here if you have a non-volatile solute, means it is not going to evaporate, it is not going to contribute to the total vapor pressure. So what exactly I mean to say is, if there are molecules here on the surface, there will be molecules of this non-volatile and non-ionizable solid as well, right? So are they going to evaporate? They are not going to evaporate. The evaporate ones are only this liquid solvents, only they are going to evaporate. So when you are adding this non-volatile non-ionizable solid to form the solution in the liquid solvent, the vapor pressure of the solvent is lowered because you are adding this non-volatile and non-ionizable solid, because it is not going to contribute to the vapor pressure of the solution. Okay, so you can say that the vapor pressure of the solution is equal to the vapor pressure of the solvent above the solution. Okay, now if we are taking P01, okay, if we are taking this P01 as the vapor pressure of pure solvent, so which is our pure solvent? The liquid solvent that we have added. And if P1, it is the vapor pressure of solvent above the solution. So we know that P1 is much less than P01, right? So what I mean to say is P1 is much smaller than P01. P1 is the vapor pressure of solvent above the solution. Okay, it is less. Why? Because you have added a non-volatile and non-ionizable solid, whereas greater to vapor pressure of pure solvent. Now this liquid solvent, I told you all the liquids have the tendency to evaporate. So we know that this liquid is going to evaporate, but this is not going to evaporate, right? Why? Because if you consider the entire solid, the entire solution, we know solution is made up of this non-volatile solid along with the liquid solvent. तो जो सॉल्यूशन का वेपर प्रेशर रहेगा वो कम रहेगा. क्यों कम रहेगा? बिकॉज देर इज नॉन वोलेटाइल सोल्यूट प्रेजेंट, एंड व्हेन यू कंपेयर इट विद द लिक्विड सॉल्वेंट, ऑफ कोर्स इट इज गोइंग टू बी more. Fine, because this liquid is going to evaporate. Hence the vapor pressure of pure solvent is much more higher than that of the vapor pressure of solvent above the solution. So P1 is lesser than that to P01. I hope this is clear. Next, the vapor pressure lowering. The vapor pressure lowering is written as delta P. Now delta P, or you even if you say delta H or delta T, if you say delta T, okay, I'm just explaining it over here. If you take delta T, then you write it as what? T2 minus T1, final minus initial. Okay, this is how you write it. So even here the vapor pressure lowering, you are going to take it as P1 naught minus P1. Why P01 minus P1? Because we know this is going to be more and this is going to be less. This vapor pressure of your liquid solvent is going to be more when you compare with the vapor pressure of solvent above the solution. So the vapor pressure lowering is delta P is equal to P01 minus P1. You need to keep this formula in mind. Okay, now there is one question that they have asked is why vapor pressure of solution containing non-volatile solute is lower than that of pure solvent. So the explanation goes same. Again, I am repeating the question if you did not understand. Why vapor pressure of solution containing non-volatile solute is lower than that of pure solvent? Okay, so the answer for the question is similar. If we take, now imagine this beaker, in that you are going to add this non-ionizable solid which is also non-volatile. If it is non-volatile, means it is not going to evaporate, and then you are going to add the liquid solvent and you are going to mix this together to form a solution. Now even when the solution is formed, you will see that the molecules on the upper surface, they are volatile liquid solvent as well, and even the non-volatile solid solute. So this is not going to evaporate, only this liquid solvent molecules are going to evaporate. So this solute particles, they are not going to contribute to the vapor pressure. That is why the vapor pressure of liquid solvent is more when you consider or when you compare it with the vapor pressure of the solution above the, or the vapor pressure of solvent above the solution. Okay, hence this causes lowering of vapor pressure. I hope you understood what is lowering of vapor pressure. Lowering of vapor pressure is done when you add a non-volatile or non-ionizable solid in liquid solvent. Now we are going to study the Raoult's law for solution of non-volatile solutes. Now that day we have already studied Raoult's law, right? Now we are going to study the Raoult's law for solution of non-volatile solutes. Okay, now we know that this Raoult's law, it gives us information about the quantitative relationship between the vapor pressure of solution and vapor pressure of solvent, right? Again I'm repeating, Raoult's law gives us quantitative information regarding the relationship between the vapor pressure of solution and vapor pressure of solvent. Now if our solution is made up of a non-volatile solute and a volatile solvent, okay, if our solution is made up of a non-volatile solute and a volatile solvent, then the law is applicable only for volatile solvent. Now what we are going to study is for non-volatile solute. Okay, now what is the statement for Raoult's law? Vapor pressure of solvent over the solution is equal to the vapor pressure of solvent multiplied by its mole fraction. Okay, if you just want me to write it here, I'll just mention it here. So Raoult's law, vapor pressure of solvent over the solution is equal to the vapor pressure of solvent multiplied by its mole fraction. Okay, this is what we have already done in the previous chapter. Now how is the vapor pressure of a solvent over the solution denoted by? It is denoted by P1, right? Just now only we did it. Okay, next is equal to, so put that sign, is equal to, vapor pressure of solvent is P0 1 multiplied by its fraction, or you can say by its mole fraction. So mole fraction, if solvent is 1 1, then it is going to be, mole fraction is denoted by x, right? So this is going to be x1. But if you remember, we know that x1 is equal to 1 minus x2. This is what we have done in the Raoult's law. So now just substitute the value of x1 in this equation. So I'm just writing that equation again. So P1 is equal to P1 naught. Now in place of x1 substitute 1 minus x2. Okay, now this will remain as it is. So P1 naught into 1 is going to give me P0 1 only, and P0 1 into x2 is going to give me, sign is going to be minus, of course, it is going to give me P0 1 x2. Okay, now P0 1 minus P1 is equal to P0 1 x2. What I did is P0 1 minus P1. Now just 2 to 3 minutes back we studied what is the lowering of vapor pressure. Okay, so P0 1 minus P1 is nothing but your delta P, which is equal to P0 1 x2. Fine. Now what can you conclude from this? From this you can say that delta P depends on x2. Okay, delta P depends on x2. And what is this x2? x2 is nothing but number of solute particles, right? x2 is nothing but, it is going to be the mole fraction of solute particles. So this x2 is of solute particles, and this delta P that is there here, it is nothing but lowering of vapor pressure, and hence it is a colligative property. Okay, I hope it is clear. First, what are we going to study? We are going to study the Raoult's law for the solution of non-volatile solutes. Okay, now previously we have studied the Raoult's law for volatile liquids, right? So this is for non-volatile solute. Now this is the statement for Raoult's law, that is vapor pressure of a solvent over the solution. This is denoted by P1 is equal to the vapor pressure of solvent, and vapor pressure of solvent is denoted by P01. Okay, keep that in mind, multiplied by its mole fraction. Mole fraction is denoted by X. Now because we are considering this for solvent, that is why P1 is equal to P01 X1. Now from the previous lecture, you know that X1 is equal to 1 minus X2. That was for binary solution, we had done it already. So next what you will do is, in place of X1 you will substitute 1 minus X2. So P1 is equal to P01 will remain as it is. In place of X1 you are going to substitute 1 minus X2. Okay, this P1 will remain as it is, equal to P01 into 1 is going to give you P01 only, then minus sign, then P01 into X2 is going to give you P01 X2. Just multiply it, maths formulas, right? Now next what you are going to do is P01 minus P1, because I told you the vapor pressure of solvent is always greater than the vapor pressure of solvent above the solution. So P01 minus P1 is equal to P01 X2. We know that P01 minus P1 is nothing but your relative lowering of vapor pressure. So that is delta P is equal to P01 X2. So from this we can conclude that delta P depends on X2. Okay, and X2 is nothing but what? It is going to be the mole fraction of solute particles. And this delta P is nothing but your lowering of vapor pressure, and this is the first colligative property. Now next we are going to study the relative lowering of vapor pressure. Now, what is this relative lowering of vapor pressure? The definition is the ratio of vapor pressure lowering of solvent, that is we are talking about delta P now, okay, divided by vapor pressure of pure solvent is called relative lowering of vapor pressure. Okay, relative lowering of vapor pressure. Now we know that vapor pressure lowering of solvent is denoted by delta P, and vapor pressure of pure solvent is denoted by P1 naught. Okay, so pressure of vapor pressure of pure solvent is denoted by P01. So the ratio means upon, right? So how are you going to construct the equation? Vapor pressure lowering of solvent, that is delta P divided by vapor pressure of pure solvent, which is P01. Okay, now but we know that delta P is what? P1 naught minus P1, and this will remain as it is, right? Now if you look at the previous equation, okay, previous equation as in this, delta P is equal to P01 X2, right? So just substitute there. So we know that delta P is equal to P1 naught X2. So if we have this delta P, P01, I'm taking the same equation, okay. If you want, you can consider that as equation 1. I'm talking about this equation, okay. The lowering of vapor pressure, delta P is equal to P01 X2. Take it as 1. So what you will do is, and this is your equation 2, and this is was equation 1. So substitute equation 1 in equation 2. Okay, so what you will get, delta P, so write that P01 X2 upon, and this will remain same, P01 only. So you can cancel this. Then what are you going to get? Delta P upon P01 is equal to X2, right? And you can even say it will be equal to X2, or it can be even equal to P01 minus P1 upon P01. Okay, so what is relative lowering of vapor pressure? It is the ratio of vapor pressure lowering of solvent, which is denoted by delta P, divided by vapor pressure of pure solvent. Okay, now we know that delta P is what? P01 minus P1, and this will remain as it is, that is P01. But from the previous equation what we have solved, we know that the lowering of vapor pressure, that is delta P, is what? P01 X2. So you will substitute this value in this equation. So what you will get? P01 X2 upon P01. So this will get cancelled. Hence delta P upon P01, you will get it as equal to X2 also, and you can use P01 minus P1 upon P01 as well. Okay, so relative lowering of vapor pressure is equal to the mole fraction of solute in the solution. Okay, so I'll just write it here. Relative lowering of vapor pressure is equal to mole fraction of solute in the solution. Okay, I hope you remember what was X1 and X2. Okay, X1 was the solvent and X2 was the solute. When we derived the equation for Raoult's law, we considered there. Fine. Now the last topic under lowering of vapor pressure is molar mass of solute from vapor pressure lowering. So we are going to derive the molar mass of solute from vapor pressure lowering. Okay, now here we are going to consider, or we are going to take 2 gram of solute having molar mass M2. Okay, so we are considering solute which is having a weight W2 and molar mass M2. Okay, dissolved in W1 gram of solvent with molar mass, it is going to be of course M1, right? Now how do you calculate the moles? So moles have a formula of weight upon molar mass. We have studied this in 11th standard, right? Weight upon molar mass. Now if I want to calculate the moles of solute, okay, moles is denoted by small n. Okay, so if I want to calculate the moles for solute, then it will come as what? N2. Okay, this is for solute, is equal to weight. So weight is how much? W2, and molar mass is how much? M2, right? So it is going to be M2. Similarly, if I want to calculate for solvent, that is going to be 1. So N1. Okay. So solvent is equal to W1 upon W2. Now, since we are calculating the molar mass of solute, we have to write the formula for mole fraction of solute. So mole fraction of solute, mole fraction is denoted by X, right? But here it is going to be X2 because 2 stands for your solute. And what is going to be the formula? X2 is equal to N2 upon N1 plus N2. We have studied this under the second chapter for your 11th standard. Okay, so this is the formula for mole fraction, N2 upon N1 plus N2. Okay, now we know that delta P upon P01 was P01 minus P1 naught, or we also knew that it was equal to X2. Okay, now here what is our X2? Here X2 is equal to N2 upon N1 plus N2. And do we have the values of N2 and N1? Of course we have the values, so just substitute them here. So in place of N2, what you will get? W2 upon M2. Okay, then N1, W1 upon, sorry, I'm so sorry, here it is M. Okay, upon M1 plus N2 is again W2 upon M2, right? Okay, now if you look for dilute solutions, or if you are considering dilute solutions, dilute solution means what? The solute amount is going to be very less and the solvent amount is going to be more. Solvent means water, right? Ata if you are saying dilute sugar solution, then sugar is going to be very less and you are going to reduce the concentration of sugar by adding more amount of water. Okay, so your N1 is going to be very high as compared to N2, right? As in the number of moles of your solvent are going to be more as compared to solute. Okay, that is why this N2 can be neglected. Okay, you can neglect N2. So in this particular equation where you will ignore N2, you are going to ignore N2 here. Why not here up? Because this is just the moles of your solute. Here this is forming a solution, so you can neglect your N2 in the denominator part. Then what you will get? What will this equation take the form as? X2 is equal to N2 upon N1, and N2 is what? W2 upon M2 upon W1 upon M1. Now if I cross multiply, then what will be the final answer? W2 M1, so that is going to be product, or you can say multiplication, and W1 into M2. Okay, so this is the molar mass of solute from vapor pressure. It is very simple. First we need to take W2 gram of solute, which is having a molar mass of M2, and we have to dissolve that solute in W1 gram of solvent with molar mass M1. Keep in mind, for solute we take the number 2 since the start of the Raoult's law, and for solvent it is 1. Okay, now we know that moles is having a formula. Moles is denoted by N, number of moles. Okay, weight upon molar mass. So if you calculate it for solute, you get it as W2 upon M2, and when you calculate the number of moles for solvent, it is denoted by N1. It is going to be W1 upon M1. Okay, it is going to be W1 upon M1. Now because we are calculating the molar mass of solute, we are going to calculate the mole fraction for solute, and mole fraction is denoted by X, and because it is solute we write the number 2 here, and the formula is N2 upon N1 plus N2. Okay, now from the previous relative lowering of vapor pressure, we know that delta P upon P01 is equal to, you can write it in two forms, that is P01 minus P1 and P01, which is also equal to x2, and we know that x2 is equal to n2 upon n1 plus n2. Then you just have to substitute the number of moles formula here. Now if you are considering for dilute solution, dilute means the solute amount is going to be very less and solvent is going to be more. Hence you can neglect n2 in the denominator part only. Why? Because it is forming the solution here. So if you are neglecting n2, then you are left with what? x2 is equal to n2 upon n1. Then you just substitute it and then multiply it. Then that is going to give you the molar mass of solute from vapor pressure lowering. So with this we have finished the first colligative property, that is lowering of vapor pressure. If you have any doubts, please do message on the group.